We are going to delve a little deeper into covalent bonds and the concepts of polar and nonpolar. Remember, polar covalent bonds form between two different nonmetals, while nonpolar covalent bonds form between two of the same nonmetals. Now, it is possible for a substance with polar covalent bonds to be nonpolar overall. Take this carbon dioxide molecule, for example. Oxygen is an electron bully. With this double bond it forms with carbon, most of the times the electrons in that bond are around oxygen. That makes this bond polar, two different nonmetals. However, there's another carbon-oxygen bond directly across from it where the electrons are also getting pulled out to the oxygens. So you have dipoles pointing in opposite directions that cancel each other out. So overall, carbon dioxide is nonpolar. The same is true for many hydrocarbons involving carbon and hydrogen. Sure, those bonds might be a little polar, but overall the molecule itself is nonpolar. We are going to talk about the interactions between covalent molecules, whether they are polar or nonpolar. One thing that we'll look at is a hydrogen bond. A hydrogen bond is not an actual chemical bond. Whereas a chemical bond, like an ionic or covalent bond, happens within the molecule, a hydrogen bond occurs between two molecules. So a hydrogen bond is an interaction between two polar covalent molecules that happen to contain hydrogen. The partially positive hydrogen from this water molecule is attracted to and interacts with the partially negative oxygen of a different water molecule. Water molecules are the absolute best example of polar molecules. The bent shape that they have means that those dipoles won't cancel out like they did in carbon dioxide. And a water molecule will always have a net dipole, a region of partial positive charge by the hydrogens, partial negative charge by the oxygens. It is the best example of a polar molecule. There is a basic rule that you should know about the attractions between covalent molecules. It's very simple. Like dissolves like. Similar types of covalent molecules will interact or dissolve in each other. A polar solvent will dissolve a polar or ionic solute because of the partial positive and partial negative charges, or the dipoles that exist. Those dipoles are able to attract each other. They're also able to attract full positive and negative charges of ions. So salt dissolves in water. Why does salt dissolve in water? Well, remember, these little water molecules have partial positive charges around the hydrogens, partial negative charges around the oxygens. So they can surround the negatively charged ions with these partially positive regions in water, and they can pull the ions out of the crystal and dissolve a crystal of salt. Sugar also dissolves in water. Sugar is a polar covalent substance. Well, water is a polar covalent substance. Like dissolves like. You can see sugar is made up of a bunch of carbons, oxygens, and hydrogens, and water is made up of some oxygens and hydrogens. They're very similar. Once again, the partial positive parts of a water molecule can interact with the partially negative parts of a sugar molecule, and the partial negative charges on a water molecule can interact with the partial positive charges of a sugar molecule, and it ends up pulling a sugar crystal apart molecule by molecule. Therefore, they dissolve. So the reasons why ionic substances and polar covalent substances will dissolve in each other has to do with those partial charges on the covalent substances and the full-blown charges on the ionic substances. Now, the rule like dissolves like, or like interacts with like, also applies to nonpolar covalent bonds. A nonpolar solvent will dissolve a nonpolar solute. The reason is they both lack a dipole. That's what they have in common. If I do an oil-based painting and I try to clean my brush with water, I'm just going to end up making a huge mess because a polar covalent substance will not dissolve a nonpolar covalent substance. If I want to clean my brush that contains a nonpolar oil-based paint, I have to use a nonpolar solvent like paint thinner. Using something like water will just end up getting you something like this. We've all seen oil and water. They don't mix. Why not? Because water is polar and the oil is nonpolar. This picture exemplifies the rule like dissolves like. These two substances are not alike. They will not dissolve. They will not interact with each other. I want to spend some time talking about these attractions between polar covalent molecules because they can end up giving some substances very interesting characteristics. A lot of the times these attractions are hydrogen bonds. I want to focus on water specifically. So we hopefully understand this diagram. I have 3 water molecules here. Because oxygen is an electron bully, it's hogging the electrons in this covalent bond, making the oxygen atoms more negative than the hydrogen atoms. So they are partially positive hydrogens, partially negative oxygens. Well, this partially positive hydrogen here could interact with this partially negative oxygen in this other water molecule. And this partially positive hydrogen from this water molecule could interact with these partially negative oxygen in this other water molecule. The solid lines you see are covalent bonds, actual chemical bonds, while the dotted lines are hydrogen bonds, interactions between water molecules. So one property that hydrogen bonds can have an effect on is boiling point. So I have some data here of some similar molecules, H2S, H2SE, H2TE. I have graphed their molar mass versus their boiling point. And you can see as the molar mass increases, so does the boiling point. We need to make a prediction about this unknown substance that has a molar mass of 18. What would its boiling point be? Following the trend, this should be the lowest boiling point. And if we look, we got a difference of 20 degrees Celsius there, a difference of 40 degrees Celsius there. Maybe this is like 10 or 15 degrees Celsius. So a reasonable prediction might be negative 72, negative 75 degrees Celsius. Well, if you look on the periodic table, sulfur, selenium, and tellurium are all in the same family, and at the top of that family is oxygen. So this unknown substance is H2O. And as we know, water has an actual boiling point of 100 degrees Celsius. The reason why that boiling point is so far off the trend of the other elements in that family is because water can hydrogen bond. Polar covalent molecules have extremely high boiling points. Another property that's affected by a substance's ability to hydrogen bond is surface tension. A surface tension is an inward force on a liquid where the molecules of that liquid want to interact more with each other than they do their surroundings. It causes them to bead up. You have a nicely waxed car and you wash that car, the water just beads up on the surface of that car. The polar water molecules want to interact with each other more than the non-polar wax on the surface of that car. You've seen a water bug sitting on top of water. That's another example of the surface tension of a polar covalent substance that's a result of the hydrogen bonds. So polar covalent compounds have very high surface tensions. I'd like to finish this video by showing you a couple examples of the amazing surface tension of water. Here's a real simple one to start with. On the left, you have about 6 drops of water. And on the right, you have about 6 drops of isopropyl alcohol. You can see the water beads up way more than the isopropyl alcohol. The reason is because the water molecules are able to form hydrogen bonds with each other. That causes them to interact with each other more and bead up on the surface of that plastic. And since the isopropyl alcohol is nonpolar, it will not bead up, and that liquid just spreads out on top of that plastic. Here's another surface tension demo taking advantage of the ability for water molecules to form hydrogen bonds. How many drops of water can you get on the surface of a penny? Layla got 24. You guys want to see a cool surface tension demo?
Yeah.
Okay, so water has a high surface tension because it can form hydrogen bonds. I'm going to take this transparency, I'm going to put it on top of there, and it's going to be able to stick. So these hydrogen bonds are even strong enough. What do you think is going to happen when I take my hand away?
It's going to stick.
Okay, it's going to stick. The hydrogen bonds are attracted to the transparency film. It's enough to keep the transparency stuck to the jar and to make it so the water doesn't come out. What happens if you think if I take the transparency out?
All the water.
Okay, all the water comes out. Right. Okay. So I like to go big or go home. So let's do it with this other jar. Let's get it filled up all the way to the top. Okay. You think it's going to be able to
No.
Yeah.
to hold all the water in?
Yeah.
Think the hydrogen bonds are going to be strong enough to hold all the water in?
No.
Yeah? No?
No.
Maybe so.
There you go, it did it. What happens when I take the transparency off?
It's just gonna go everywhere.
All the water's going to go everywhere?
Yeah.
Wait, what?
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 What happened there? What? You trying to look under there? Why don't you look under there? Get your face all the way under there. Look at it.
No.
Why not?
It's gonna just come up.
No, it won't. Get your face under there, Ike. I tricked you. I had a little screen on the jar. So the surface tension of water was strong enough when all the openings were really small. But then when I turn it sideways, the surface tension gets broke by the screen and all the water comes out. Is that a good demo?
Yeah.
Like that one?
Yeah.
Except the part when I get it.
Ow!
Want to see another surface tension demo?
Yeah.
All right. I'm going to do the same thing we did with the jars with this glass here. Is it going to be able to hold it up?
Yeah.
No.
Yep. Okay. Now I'm going to put that glass on top of there.
Oh no.
I'm going to take this out. I'm going to take the film out. Is the water going to stay in there?
Yeah.
Yeah.
All right. How can I get the water out of the top glass without touching it? What do you think?
Pour more water on it.
Pour more water on it? What do you think?
I don't know.
All right. I'll show you.